So far, we're in the unidimensional world where theta, or the parameter of interest, is a scalar. Let's now turn into the multidimensional world and introduce the Gibbs sampler. The Gibbs sampler is a very well-known method that can be used for Bayesian parameter estimation when our unknown parameter is a random vector. The Gibbs sampler can be thought of also as a special case of the Metropolis-Hastings algorithm with a particular proposal distribution. For now, let's forget about Bayesian and introduce the Gibbs sampler to draw from a target distribution f in general. Let's suppose that the vector x, which is x1 all the way up to xd, is a d-dimensional random vector with probability density f, and f is our target density. Further, let's let x minus xj to denote all of the entries of x excluding the jth dimension. By doing this, we will be able to specify the conditional probability density function for xj given the other dimensions x minus j. Let's denote the conditional distribution of xj given the rest of the dimensions by fj of xj given x minus j. Later on, I will just call this conditional density fj. Gibbs sampling involves drawing the individual components of x, in other words, each of the j dimensions of x from the fj densities. When we sample from xj, the Gibbs sampling algorithm sets the proposal distribution to be the conditional distribution of xj given the rest of the dimensions. By using this particular proposal distribution, it can be verified that the resulting acceptance probability is 1, meaning that there is no need for an additional acceptance rejection step like the MH algorithm. Let us formally describe the algorithm for Gibbs sampling. Again, let's suppose that bold x, which is a d-dimensional random vector, follows some distribution function f, and f is the target density that we want to obtain samples from. We will start from initializing the value of x, x0. Let us use x0 to denote the initial values of each of the d dimensions for x. For each subsequent iterations, t from 1 to some large n is the chain length, we will first set small x to be equal to the last iteration's x. And then for each dimension j from 1 through d, we will generate the jth coordinate x star jt from fj, the conditional distribution of xj, given the rest of the entries inside the small x. In other words, depending on the current values of the other dimensions, we will generate the jth coordinate. Following this, we will update the jth entry of x, which is denoted xj, to the value that we just generated, x star jt. At the end, after we iterate through each of the dimensions, generating each dimension's x by conditioning on the current values of all of the other dimensions, we will set the tth draw of x to be equal to this updated small x. Let us see an example of drawing from the bivariate normal distribution. Back in week 2, we used the Cholesky decomposition of a covariance matrix to transform independent draws from normal 0, 1 into draws from the multivariate normal distribution with mean mu and covariance sigma. This time, instead of using the Cholesky decomposition to draw it, we will try to develop a Gibbs sampler to do the same thing. In other words, to obtain samples from a bivariate normal distribution. Let x, which is equal to x1 and x2, 2 dimensions, be bivariate normal with means mu1, mu2 for the 2 dimensions, variances sigma 1, sigma 2 for the 2 dimensions, and correlation between x1 and x2 that's equal to rho. In the case of bivariate normal, we know that the conditional distribution of x1 given x2 is also normal. Specifically, x1 given x2 is normally distributed with mean equal to this mu x1 given x2 and variance that's equal to this sigma squared of x1 given x2. So let's denote the density for this normal distribution. So the conditional normal distribution of x1 given a particular value of x2 by f1. We can do the same thing for x2. All we need to do is to exchange the indices and make it x2 given x1. What we're going to do is to construct a Gibbs sampler so that the stationary distribution is the bivariate normal distribution we like. In other words, the stationary distribution is bivariate normal with mean mu1, mu2, variances sigma 1, sigma 2, and correlation rho. To do this using Gibbs sampling, we first need to initialize x. Let's set x0, which is equal to x10, and x20 to some particular initial value. In each subsequent step, we will first generate x star 1 star t. We first update the first dimension, x1, by drawing from the conditional distribution of x1 given the current value of x2. The current value of x2 is given by x2 t minus 1, so the x2 sample from the last iteration. And then we will update the second dimension. We will set x star 2t to be equal to be a sample from f2 of x2 given x star 1t. In other words, we will generate this sample from the conditional distribution of x2 given the sample that we just obtained for x1. And then at the end, we will update our x, where the tth iteration of x is just equal to the two values that we generated. We will implement the Gibbs sampler to generate from the following binary normal distribution, with the mean of the first dimension given by 0, mean of the second dimension given by 2, the standard deviations are 1 and 0.5 respectively, and the two dimensions are correlated at 0.75. One thing you should notice is that the conditional distribution, the conditional variance of x1 given x2 and the conditional variance of x2 given x1 actually do not depend on the particular values of x1 and x2. You can see that the mean x2 actually affects the mean, the conditional mean of the distribution. However, the conditional variance, which is 1 minus rho squared times sigma 1 squared, actually does not depend on the value of x2 or the draw that we just obtained. In other words, we can calculate that beforehand. Let's first calculate these guys. So sigma of x1 given x2 and sigma of x2 given xy. Let's call them S1 and S2, given by the formulas that I have previously shown. After doing this, we will initialize the x1 and x2 to be mu1 and mu2. In other words, we'll set the initial value of x1 to be equal to the mean of the first dimension, and then the initial value of x2 is equal to the mean of the second dimension. We will run a total of 5,000 Monte Carlo iterations, and we will use the X matrix, which is currently a all-zero matrix, to store the MCMC draws. The matrix has two columns, which are used to store the draws for x1 and the draws of x2. And since we set the initial values to be the two means, we'll set the first row to be the mu1 and mu2. Subsequently, for each subsequent iteration, we will first compute what is the mean of the normal distribution of x1 given x2. This is given by mu1 plus rho times sigma 1 divided by sigma 2 times x2 minus mu2, where x2 was the last draw of second dimension we got. And then after we get the mean, and we have computed S1, which is the standard deviation beforehand, we will generate the next sample of X1 to be a normal distribution sample with mean M1 and standard deviation S1. After updating the first dimension, we'll update the X2. Similarly, we compute M2, which is given by mu2 plus rho times sigma 2 divided by sigma 1 times x1 minus mu1, where x1 is the draw for the first dimension we just obtained. And then, given this particular mean and the corresponding standard deviation S2, we will generate the next sample for the second dimension. And that's given by our norm with mean M2 and standard deviation S2. We iterate this for a total of n times. And let's take a look at the results. Let's first look at the mean, standard deviation, and the correlation of the draws after tossing away the first 1,000 iterations as the burn-in cycles. In order to look at the means of the two dimensions, we can do co-means of rows 1001 to 5000. This will compute all of the burn-in averages of the first column and the second column. We can see that the mean that we get for our draws for x1 is quite close to the theoretical mean of 0. And then the mean for the second dimension is close to 2, which is the target distribution we like. We can also look at whether the standard deviation is close to the theoretical values we want. As you can see, the standard deviation of the first column is around 1, and the standard deviation of the second dimension is around 0.5. So yes, they are quite close to our target. Lastly, we can look at the correlation among the two dimensions. And this is quite close to the value we want, which is 0.75. We can also look at the scatter plot for x1 and x2 in the post-burn-in iterations. This can be done by doing plot of the 1001 to 5000th dimensions rows of the X matrix. And you can see that it does appear these are normally distributed with a correlation around 0.75. So we're going to come back to Gibbs sampler at the end when we discuss a Bayesian application. However, for now, let us just leave a few remarks and move on to the next topic. For the example on the bivariate normal, the target density is a bivariate normal distribution. As you can see, we're not yet generalizing this to the Bayesian framework where we are interested in a posterior distribution that's the target distribution. Later on, when we look at the application, we'll see an example where the target density is the Bayesian posterior of model parameters. Another thing to note is that in this example, x1 given x2 is of a well-known distributional form. So we know that when two things are distributed bivariate normally, then x1 given x2 is also normal, and so is x2 given x1. In practice, it is quite possible that xj, given the other dimensions, is not a well-known distribution, and it does not even have a closed form density. What should you do? Well, in these cases, we can still implement the Gibbs sampler, but we will need to use something called Metropolis Hastings within Gibbs sampler. In MH within Gibbs, we use an MH step, where we sample from a proposal distribution and then accept or reject with some probability for drawing each of the dimensions, xjt's. So when when the conditional distribution of xj given x minus j cannot be directly sampled from, we can first sample from a proposal distribution and accept that draw with some probability. We're not going to cover MH within Gibbs in this class. If you're interested, you can look it up, and the procedures are actually quite straightforward.